have another line. And we have also from Banach fixed point theorem this statement. So this is a combination of ordered relation and metric relation. Very nice theorem. Very nice theorem. I'll go further. So this is 2004. Then, almost immediately, these two Spanish authors extended. It is important, the reaction. So sometimes people are reading all papers which are published immediately after they are published. Sometimes it is very good to do this. So they were the first to read, and they published these two papers. This was published later, but they produced at the same time. You can see they use contractive mapping theorems in partially ordered sets and applications to ordinary differential equations, and almost the same, but existence and uniqueness of fixed point in partially ordered sets and application to ordinary differential equation. In fact, they used in the first paper the monotone case for non-decreasing mappings, and in the second paper, non-increasing mappings. So in the sense of the partial relation. So partial relation is involved in this monotonicity. I'll come back at a certain moment, and I'll show you these concepts in great detail. For the moment, I just want to tell you the following story. This was published in 2004, the paper by Gran and Raurings. But after a while, the mathematician, the specialist in the area, Professor Kamsi, by the way, Professor Kamsi, he discovered that the same principle has been established, you can see how many years ago, before this result. But this is a Romanian mathematician, very strong mathematician. His son is also very good mathematician, but his son is working in France, and he's in Romania. Why this result was had no impact? Because I'll show how impact had this theorem by Ran and Raugring. Huge impact. And this one, very little impact. Because this mathematician, Turinic, always he's writing his results in the most general and complicated way. So he stated the result not so simple like here, not so simple, sorry, because here is very simple, clear, crystal clear. We have a map, we have this contraction condition, we have this initial relation between the first two iterations, because this is the idea. This is x1, and so either x1 is less than x0 is less than x1, either x1 is less than x0. So this is very nice. But this paper by Turinic remained unknown for a while, until Professor Kamsi told me, look, this famous theorem, because this is now famous, if you will look on this, the citation, it has hundreds, maybe 1,000 citations. Very cited paper, because it was very simple and people noted this result and continued to work. Then, what next? Bhaskar and Lakshmikantam unified the two papers I mentioned before, and they established a fixed point theorem. So I said, Nieto and Rodriguez did for increasing mappings in this sense. Then in the second paper, for decreasing, so this is U in this relation implies this, and U in this relation implies this. This is increasing and decreasing maps. And what did Bhaskar and Lakshmikantam? They took a map of two variables and introduced what is called mixed monotone. So is increasing with respect to the first variable and decreasing with respect to the second variable. And then they unified the results obtained by Nieto and Rodriguez, and they gave an application. Again, the history repeats. The paper by Nieto and Rodriguez had no very significant impact, but this one had an extraordinary impact. If you look in any database, I collected, I had a look just yesterday, it has almost 1,000 citations, this paper. Almost 1,000. Very, very successful paper. Even if it is just unifying these two results by Nieto and Rodriguez. They just do this. So you see, all the time we should think what we can do. And they were very smart, very lucky to see that they can unify this into a unique map F, into a unique map F. So I discovered this result very late, let's say maybe 2010. I found the paper and I read, I said, these coupled fixed points are interesting. And I started to study. So again, I repeat the definition of a coupled fixed point. This time I use X and Y. So we have a map F defined on the Cartesian product of this set X. XY is a coupled fixed point if we have this relation. So look, this is related to the notion of fixed point for a map defined on a product. This Serbian mathematician, Prešić, in 1965 considered such kind of mappings, and he established results to ensure that we have a fixed point. This means X bar is F of X bar X bar. If we compare this definition, what does it mean? It means that a coupled fixed point is a fixed point if X equal Y. So in this sense, these results are also related. This was in 1965. Well, again, these mathematicians, Rahn and Reurings, Nieto and Rodriguez and Bhaskar and Lakshmikantam were not the first one to do this. So they were not the first one, and this is very interesting. The first paper on this topic appeared to be this one. Look, I found by chance, I read a little bit in Russian, but just a little bit, just to understand the mathematical text, and I was lucky that my elder brother was 4 years my senior, and when he started to study Russian, he was upset for his teacher, a lady. She was a neighbor of us. She all the time was telling to my mother, look, he is not good, he is doing this, and she was very upset, and she declared, I don't study Russian language. So he told me, I was in first class, he told me, please do my homework in Russian. So I started to do his homework when I was in first class, and this is the reason I learned Russian, and I can read any text in Russian. Maybe I continued some 3 weeks, maybe a month of doing his homework, and I just started to learn the alphabet. Russian alphabet is difficult to read, like Hindi. It's very difficult. And in this way, I found this book. You can see it is published in Russian, and we can see it's about nonlinear systemostatics. It used exactly the same problem. This is coupled fixed point problem. And he also published some papers before, and these are the papers he published about these coupled fixed points, and he combined it order relation on sets with contraction text. So he is at least so far I know that he is the first one to study coupled fixed point. But just in my papers I mentioned this name of Opoitsev. Opoitsev is the name of this Russian mathematician. And okay, I started to work on coupled fixed point theory, and here it's a kind of genealogy. I asked to one of my students to do this, and you'll understand how fixed point theory develops. Look, Banach established his fixed point theorem in 1922. Tarski, again a Polish mathematician, he's also from Poland, he established this fixed point theorem I mentioned you on a complete lattice. A monotone map has at least a fixed point. This is ordered fixed point. Please check. I sent Professor Murti the file of this book, great book of Professor Rus, and you'll find there Tarski theorem and many other things. And then what appeared to be Rane-Röhring's unite is, but Opoitsev did this, then Nieto and Rodriguez, but here I put Opoitsev, he remained unknown until I published some papers and I mentioned he was the first one actually. So you can see these years and how many? Well, lot of years. So 20 years after, more than 20 years, almost 30 years after Opoitsev was doing Rane-Röhring's. Of course, we cannot cover all literature on mathematics when we are documenting. And then Bashkar and Lakhmikshkatan this theorem in 2006, and I and my PhD student, we did in 2011 on triplet, then with my friend Karapinar on quadruple, and then a lot of papers were coming. And of course, before this paper by Bhaskar and Lakshmikantam, he was doing the same thing for other classes of mappings, but only monotone without using contractive conditions. So this is the story of couplet fixed point theory till now. Then from here it continued with hundreds of papers. So I like this, this diagram because it is very useful. I do recommend you, when you want to systemize some results, to do something similar. You will understand better the things. So we go back to the notion we need for our theorems for couplet fixed point. So we are in a partially ordered set. F, this set defined on the Cartesian product of x and x, has the mixed monotone property if F is non-decreasing with respect to x and is non-increasing with respect to y, which means this inequality. So x less than x1 less than x2 implies this for any y, and this one y1 less than y2, we say in relation to y2 implies this one. So this is a mixed monotone property. This kind of concept has been introduced by Bhaskara and Lakshmikanta. And here is the simplest example possible. This is increasing with respect with s, so is monotone, non-decreasing, and is decreasing with respect to y, and the unique fixed point is this point 2, 2. It's fixed point, and it's also couplet fixed points. Another example is this one. So it is possible to have more than one couplet fixed point. And look, these are fixed points in the sense I mentioned. They are x equal y, but this is a couplet fixed point because x is different of y, and there is another one, the pair. So these are, for such a map which is mixed monotone, we have two couplet fixed points, well, actually four couplet fixed points, but two of them are actually fixed points. This is these are the simplest examples. So coming back to the theorem, I'll put all to read together. The merit of Rahnen-Röhring's theorems and of Nieto, Rodriguez, Bhaskara, and Lakshmikantam is that they combine monotony and contractive conditions. I will suggest you to think about, because some of your colleagues asked me yesterday or 2 days before a question regarding relation between accretive operators and contractive. And my answer was that Browder did this. Browder was the first one to show the relation between monotone type operators and contractive type operators. And it is known, for example, that monotony corresponds to non-expansiveness, strongly monotony corresponds to, and another property corresponds to contraction, and so on. So this is the merit. My idea is that here monotony is imposed separately of the contractivity. I guess some insights could be done having in view this equivalence. So the main theorem by Bhaskara and Lakshmikantam is this one. We have a partially ordered set, we have a metric D on X, and XD is a complete metric space. We have a continuous mixed monotone map F such that we have this condition. And you can see this is similar to the contraction condition, but here we have f of xy, f of uv, And here we have a distance between x and u and distance between y and v. Only for comparable elements. So only if x is compared to u by this partial relation and y is compared to v by means of the partial relation. Be careful. This symbol is not the same. I did not put, normally we should denote this relation by some index to differentiate, but here is the less than or equal is between numbers, between numbers because the distance is a positive number and so on. But here these are the refer to the partial order in this set X. And then if we can find a pair of points x0, y0 such that we have either this or this, then we are sure there exists a coupled fixed point of f in the sense we have this two equalities. This is the theorem by Bhaskar and Lakshmikantam, and we can look it in this way. What are the elements? I told you that it is useful to look carefully to some results, and you can do in this way. What are the mathematical objects and the main properties involved in this theorem? So these are a partial ordered set, a metric, complete metric space, an operator with two properties, mixed, monotone, and continuous, a contractive condition, and an order relation between the first two iterations. So in the presence of all these contract conditions, we get the conclusion. And here it's the application. How long can I be? Sorry, Professor, the time. How long? Until 4 o'clock? Yeah. Okay, so all right. Do not compress my presentation then. Yeah. So here's you'll have access to my presentation. So I just keep here. This is the result established by Bhaskar and Lakshmikantam. They consider this simple problem with some assumptions, and they succeeded to prove that if we have this condition 9, then the problem has a unique solution. And what to do with this theorem? When we read the theorem, we can try to weaken the contraction condition, to weaken the properties of F. All elements I mentioned before, the generalized, the ambient space, weaken the initial condition, extend area of applications, and to do various combinations. So this is the paper by Bhaskar and Lakshmikantam, and some other papers which were dealing with the two-point boundary value problems. I mention here just a few. Among them is this paper I published on this subject. There are many other papers inspired by this theorem. I put here just a representative of them. They were published, and several authors were applying the same technique to various differential equations. So I started to look on this theorem, and I tried to improve this. It was related in some sense with another topic we were studying with my collaborators, and in the end I asked myself, how large is the area of applications of these results? Is this theorem really useful in applications? And Here it's a very elementary example. This is from my book. This example is taken from my book, I told you, Exploring, and so on. And this is a system of nonlinear equation which is not easy to solve if you are not familiar with special techniques. Here we have f, this function. F is continuous, is strictly increasing with respect to x, is strictly decreasing with respect to y. It has this point which satisfies these two conditions in the theorem of Bhaskar and Lakshmikantam. So the unique solution for 4 should be obtained by Bhaskar and Lakshmikantam theorem. But since the coupled fixed point is this one, y is equal to x is equal to y, we can apply this Prešich fixed point theorem, which was obtained in 1965. A second example, this one. I take this very simple function, which is mixed monotone, it's continuous, and we want to see if it fulfills the conditions in the Bhaskar and Lakshmikantam fixed point, coupled fixed point theorem. So assume we can find such a k less than 1, and we have this inequality which appears there, and we are conducting to this, and we can see we get this contradiction 6/5 less than 1. So their theorem cannot be used to solve this simple how is y? This is a very trivial system, but their theorem cannot be applied to this because this condition, contraction condition, is not satisfied. What does it mean? It means that this contraction condition is too strong. So we should try to weaken the condition in the Bhaskar and Lakshmikantam. I go back. It's easier than to write on the whiteboard. Just allow me to go back to it and show you again this condition. This one. So this is condition by Bhaskar and Lakshmikantam. This one. Okay. Now, I was trying to see what's wrong here. How could improve this result? Because it is easy to see that if we consider the coupled fixed point associated to this problem, I already wrote, we have a unique solution, which is the coupled fixed point and also the fixed point of this map. And this is the result of this investigation. So the result is an improvement of the theorem by Bhaskar and Lakshmikantam, and look to the conditions. X is the same partially ordered set, D is a metric, XD is a complete metric space, F is a mixed monotone mapping, nothing about continuity, you can see, there is nothing. So I dropped the continuity condition at this moment. And instead of having that condition only this term, I added another one which is in some sense symmetric. And instead of considering k over 2, I consider just k, and because I have here two terms. And the rest of the theorem is exactly the same. If we can find x0, y0 in this way or in this way, then for sure we can say that this map, this function f, has a coupled fixed point x bar, y bar. This is the result. And now I want to see, to compare the two conditions. Sorry. This is condition of Bhaskar and Lakshmikantan, and this is my condition. What is